see.
Yeah, that's the total.
Where did I put my?
Or the total computer science majors.
So let me see. Let me catch up. I'm behind. Let's see. All right, so everybody did that. So I pretty much will give you a problem like this and have those blank spots outside. So at least it kind of spurs your memory if you're like, holy shit, okay, I got to fill those blank spots in. Those are all the totals I need. What's the only problem that I have with talk? What's the only problem where the bottom isn't going to be 176? Because E is the only one I'm given information. Therefore, I know something. Therefore, the number of people it could be will decrease. Everybody else should be out of 176 to start with. So probability of 10's gross mod, of course, is going to be 126 out of 176. What do you guys get for that? 715.9. Or you can make it 71.59%. So this is your work. This is your answer. And then if you want to make it a percentage, go for it. Something else that freaks me out is people sometimes think that these build on each other. B is its own problem. You kind of restart. What's probably get a business major? 92 out of, and what do you get there? Sorry? 5227. So if you do 92 divided by 176, I like it. And real quick, you know this is going to be, what's twice 90? Which is bigger than this. So you know it should be bigger than 50%. You guys see that? It's more than half of what the bottom is. I like it. Here's an OR, so the top should get bigger because of that, but you got to be careful, don't make it too much bigger. So if I do, so let's see, there's a few different ways I could do this. I could do 126 Grossmont plus 73 computer science majors, but then I've counted how many twice? 62. Or you could, of course, just say 126 Grossmont students plus there's 11 computer science I haven't counted yet. Does that make sense? If I count all these people, how many computer science people have I not counted yet? 11. And of course, what's 73 minus 62? Freaking 11. So either way you do it, the math is going to come out right. And what do you guys get for that? 7784. Okay. Yes.
Yeah.
What happened?
Was we supposed to round 5227?
Maybe. You can bring it up. Did you see me do it? I'm crowdsourcing. So let's see.
So we was supposed to round.
Hold on.
Oh, that's right.
92 divided by 176. I get 5227. What's wrong with that? What's the next number after 7?
2.
So why would I do anything with that? Right? How does rounding work? If the next number is 5 or more, you make that number go up. If it's not, you leave it. I like it. So is 72 closer to 70 or 80? It's closer to 70, so you leave that as a 7. Yeah. Is that cool? Is that all right? I like it. And should make the number smaller. And one reason why I haven't shown you the formula for and yet. And the minute I do, people start doing this one using the formula, and that is disgusting as all shit, right? I'm not saying the formula's bad. I'm just saying it's not smart to use it in this situation. Because I can see how many math majors are also Cuyamaca students. How many? 2. 2 math majors are also Cuyamaca students. Out of, yeah, I don't know what the hell is up with the students, so it's got to be out of 176. I like it. I never know what the hell's up with students.
0.0.
Say it again.
0.0114.
114?
Yeah.
Okay. All right, here's finally the only one where the bottom changes. What will the bottom become now?
73.
Yeah, because it's given computer science major. And out of those, how many are Grossmont students? 62. So that is now point
8493.
8493. Become a point. Okay. Now, I don't care how much I say this, and I understand this is not immediately obvious, but it's a little bit more direct than people seem to believe, ever. What's the probability somebody attends Grossmont?
0.7.
Yeah, almost 72%, right? If I know they're a computer science major, does the probability they're a Grossmont student change? Look at the number. What was it? If I know they're a computer science major, does the probability they're a Grossmont student change?
Yes.
Yes. Yes. See that? If I know they're a computer science major, the probability they're a Grossmont student increases. So knowing they're a computer science major affects the probability they're a Grossmont student. Doesn't it just make sense? I would call those dependent. One affects the other one. So the way to answer that question, the more words you use for this kind of question, the more wrong you are. You can't explain this with a, well, you could be a Grossmont student and you've said too many words. This is a very mathematical idea. So the probability of Grossmont is not equal to the probability of Grossmont given computer science. Since that's not true, that they're not equal to each other, and show me 0.7159 does not equal 0.8493. So therefore they are dependent. When does that word end? There it is. The probability they're a Grossmont student changes if I know they're a computer science major. So then, of course, we're going to call those dependent events. So here's a beautiful question. What the shit is an independent event, Jeff? Show me 2 independent events. Okay, I will. I'll show you right now. So we got that. How well do you guys, anybody really not know cards at all? Do you guys know how many cards there are in a deck of normal cards?
52.
52.
Oh my God.
You're all right. You might have taken the jokers out and just took too many. I don't know.
Oh, okay.
So no jokers, but that still leaves 52 cards. How many suits? Right? Do you know what they are? Don't start doing Lucky Charms, but hearts,
Diamonds, clubs, spades.
blue diamonds. Let's see. Hearts, diamonds, clubs, spades. So if you divide 52 by 4, you get 13 of each. Is that cool? Lucky number 13. All right. Yes, yes, maybe, maybe. So now watch this. Now, of course, the cards for each suit go from what to what. Let's say ace is low. Where's my poker players at? Anybody play any poker?
Yes.
Ace can be high or it can be low. So I just want to make it low. Oh, yeah. So that's just the way I am. So ace is like 1, 2, 3, up through 9, 10, jack, queen, king. Is that all right? So that's 13. Okay, so what's the probability if I pick a card that I get a king? How many kings are there? 4, right? There's a king of hearts, king of diamonds. Out of how many cards?
52.
What's the probability I pick a king given that it's a club? 1 out of 13. There's 13 clubs and there's only 1 king. What is 4 out of 52 reduced to? So, knowing that it's a club, did it change the probability that it's a king? Nope. Therefore, clubs and kings are independent events. Knowing one does not change the probability of the other one. Why does that make sense? Because if I... You ready? Watch this. If I say clubs, I've thrown out 3/4 of the deck. Do you guys see what I mean? If I say clubs, I've thrown out hearts, diamonds, and spades. I've also thrown out 3 out of 4 of the kings. So the ratio stays the same. If you don't know what I just said, I'm fine with that. It's okay. It was some extra shit. The fact that the probability I get a king stays the same if I know it's clubs, that tells me those are independent. So how often are events truly independent? Not very often, to be honest. But just in case you're curious, it can be close enough to say it's basically independent, but we're not going to get into all that detail here. Okay. All right, so any questions on that first one? We're not going to finish this today, by the way, but we are going to get through number 2. This is going to leave the Brussels sprout and the chocolate milk one for later. Sounds like a great lunch. Brussels sprouts and chocolate milk. All right, sorry for that. So, this next part. Before I do the algebra, I want to do some silly examples. Let's investigate. Well, one of them's really not silly at all. Let me start with that one. And then I'll do the one that's really silly. All right, stay with me. So what we're going to do is going to kind of backtrack a bit. I want to investigate. There were 2 formulas I haven't written yet. We have a formula for OR, right? Do we actually need it? Not yet. We will on the third one. The third one I can't do without formulas. But we haven't done the formula for given yet, right? And we haven't done the formula for and yet. Correct? Okay. So let me do a formula for given. Then I'll do my silly examples about and then we'll do the algebra to get the and formula. Oh shit. Well, did I mean to do that? David. Let me help me out. Why did I just erase that? What was this? This was 91 students 11. Okay. So we're gonna kind of create this formula the same way we created the OR formula. We're gonna look at what we did and write it down in general. Where'd that 91 come from in this problem? It came from the which piece? The given piece, right? So on the bottom is going to go the probability of the piece that's given. So the bottom is going to be related to the given thing. Sorry. Got to leave him awake for now. Maybe I should put this up here. I'm going to take this away. We don't need all this. Yeah. Let me put this up here. On the bottom is the probability of the given. The bottom is the given piece. Now, what was the top? The 11. Of course I just erased the stupid table, but where'd the 11 come from? Those are the people that were what?
That were both.
Both. So they were students and people that said yes, right? So on the top is going to go everybody that's this and this. In fact, a really nice visual of this. You guys have seen this kind of picture before? It's called a Venn diagram. So watch this. If I know that B happened, given that B happened, do you see that? So I know that something in here happened. What's the only way that something in A could also happen is if it's where? Could that have happened? Hell no. Where's the only part of A that could have happened? The part that's in here. And what is this? That is A and B. Shit. There you go. So the basic idea of probability. Well, how many match what we're looking for? All these. And how many out of what? Well, those, because that's what happened. So that is the formula for given. Did I actually need that formula to do the problem? No, because I gave you a problem where you can count everything. If I can count everything, I don't need any damn formula. Can't like it. Might be just me, but that's all right. Okay. So before we do the and formula, I want to lay the groundwork for why it's going to make sense what we see. Here's the not so silly. This is the really sad. This involves little Jeff crying. Do you guys know how many times, I hate that I say this now, how many times the space shuttle has exploded? Of course, they stopped the whole shuttle program. You guys know it's exploded more than once, right? Do you guys know that?
Yes.
So the first time, and again, I hate that I have to say the first time, was back in '86. Jeff was 14. He was in English class. I'll never forget this, sitting in the first row. I was in Florida. We used to always go out and watch the shuttle take off, but for some reason, maybe it was cloudy, I don't know, we didn't go out. So I'm in English class, I'm like, I know it's taking off now, man. Yeah, sure, let's talk about this poem. And nothing wrong with poems, by the way, by English colleagues. Then over the loudspeaker or something, I think they said something about the shuttle blowing up, and I just started crying because I was like a major geek about shuttle stuff, and oh my god. All right, do you guys know? Does anyone know why it blew up? So here it is. But figuring out why. So in the fuel line for the space shuttle, there were these things called O-rings. Shit, just living. O-rings. They were like valves. So they didn't think it would be bad if the valve malfunctioned and the gas flowed the other way. So why do you think they have several in a row? Just in case. Why would you have several of them in a row then? If you just had one and it malfunctioned, you're gone, you're dead. But if one malfunctions and you have several of them, you're okay. So, you guys all right? You guys with me? You guys okay? Are you guys, what happened? Everybody's like, no idea. It is a valve. Everybody cool with a valve that makes things go only one direction? So if it does not work, it's bad that it goes the other way. So you have multiple. If you live in a bad neighborhood, what do you have multiple of on your door? Locks. Very often multiple types, because you're like, if you're going to get in here, you're going to have to like show me you belong in here. You got to be really good. You pick that lock? What about this one? Oh shit, what about this one? And I can say it because I lived in somewhere where they had multiple locks and bars in the windows. But it was cheap, and I survived, so hey. Why do you do that? Why do you have multiple locks? It can't be the same as OR, because OR adds probabilities. So if they had a 1% chance of picking this lock, and I put three of them total, if I added, now they have a 3% chance of getting that. Didn't help me out. No, so that can't be how it works. So, coming back to the O-rings. Let's say there's a 1% chance that one of them will malfunction. You with me? So if you have 3 in a row, what's the overall chance that all of them will malfunction? Well, watch this. You ready? 1% of the time, this one malfunctions. Of those times, how often will this one malfunction? 1%. Of those times, how often will this one malfunction? 1%. What's 1%? What's of me? Times. So, and this one malfunctions, and this one, and this one, and seems to mean multiply. Which is kind of counterintuitive, but when I multiply numbers that are between 0 and 1, the result gets smaller. We're used to multiplying making things bigger, but between 0 and 1, it makes things smaller. You guys with me on that? So what is that? 1, 2, 3, 4, 5, 6 zeros. So that's a pretty damn good, I feel pretty good about that, right? If I had that chance to die in surgery, I'd be like, that's could be a lot worse, holy shit. Right? You guys semi with me? Okay, semi. So that's the idea so far. It seems to be multiply. I like it. Here's the silly example. So this one, if I wanted to join I always say the wrong thing because if I wanted to join a fraternity, or if you want to join a sorority, right? And let's say it's Sigma, Sigma, Sigma. I'm going to do this. They have a hazing ritual that's not something that will get them in the news. It's nothing, nobody gets hurt. You with me? So that was big a while back. In fact, it was at my old school where there was one incident. But what they do is I have to walk down this long hallway, and every third step I take, somebody slaps me on this cheek. And every fifth step I take, somebody slaps me on that cheek. You with me? How many, so every what many steps will I get slapped on both at the same time? Every 3 steps, bam. Every 5 steps, bam. So 1 out of 3 chance for this, 1 out of 5 chance for this. How often do I get slapped on both at the same time? 15. What's 1/3 times 1/5? 1/15. So 1 every 15 times I get slapped on both. That was hard. It wasn't too hard, but it was harder than I meant. You guys, does that make any sense? So again, that's a silly example. There's the more somber example, but basically and seems to mean multiply. Now watch the algebra catch up with what we just discovered. So taking this formula right here, how do I solve? Right here, I can make a formula for and because there's and. What algebra could I do to this to get the and piece by itself? What can I do to both sides to get the probability of A and B by itself? Yeah, multiply by peanut butter. Right? So now I have a formula for and. And to be honest, it could actually be this way too. Doesn't really matter. Well, that's the part that I knew there was something I forgot. So about the spatial one, why did it blow up? Because that morning it was icy. And they were arrogant because they had blasted this thing off and we had been lucky as all shit. That morning it was icy. The O-rings don't like the ice. They have a higher chance of failing, and that's exactly what happened. Right? And then Jeff, the rest is history. Jeff cried. Yeah, so look, it means times. It means times. Now notice that or is basically add, but it's got an adjustment, right? I got to subtract any that might be both. The and is basically multiply, but its adjustment is this given piece. So let's see how this works. Let's go back to cards to do a problem real quick. Oh, did I do that? Yeah. Where's my camera? Are you facing the right way? All right, stay with me. So we got a deck of cards. But this time I'm going to pick 2 cards. And I'm going to do it in a very specific way with replacement. It's a very strange day for talking for me for some reason. Okay. Yeah, this will help, whatever this liquid is. Nasty stuff. All right. What the hell does with replacement mean? That means if I pick one card, I'm going to put it back in. If I picked a card and threw it away, and then I went to pick another card, you guys see how the probabilities change? Because now I've got 51 cards. Oh, shit. So if I do it with replacement, what's the probability to get 2 kings? So here's how I look at this. I have 2 things. One thing I want to happen, and means multiply another thing. So if I wanted to pick 3 cards, I would put 3 empty spots. So sort of like a hangman game. Why do I have a times in the middle? Because that's what and basically means. It means times. What's probably the first card's a king? We did this one already. 4 out of 52, right? 4 kings out of 52 cards. And then I put that one back in. What's the probability I get a king on the next draw? Still 4 out of 52. I still got 4 kings. Still got 52 cards. Right? Whatever the hell that is. I feel like I should know. I've done this enough. 0759? No. This is true, because it's 113 times 113. But what's the decimal?
0.0059. 36 over 52.
0059?
Yeah.
Okay, all right. All right.
He divided every single one of them. How did he do that?
How do you mean?
Just don't divide. You don't time straight across because the number's the same, right? Or how do
All right,
you do
real
it?
quick. The only time I need like denominator, that I need them, is when I'm adding, subtracting, because that's when I need like terms. Like denominators is like terms. That's it. When I multiply, I don't need like terms. So don't say 452 is 16 out of 52. That's not true, because then I'll go 52 times 52 is equal to 52. But you don't have to show me the intermediate step. You don't have to show me 16 over whatever the hell this is. 2604. 2704? Damn. So close. All right. That's all you got to show me right here. This is the work. That's the answer. I like it. Let's do, this gets kind of boring, but if I do another one, it's going to be the same answer. Watch. 8 and then an ace. Why is it the same answer? Yeah. 8's got a 4 to 52 chance. Anything's got a 4 to 52 chance. Any specific type of card, right? So it's still going to be 005. Now, here's where things get interesting. That was neat. Air kicked. All right. What if I pick two cards without replacement? Was probably get a king and then a king. Yeah. So there's still going to be two spots. There's only two things I'm doing. The first being a king would be 4 to 52, and then I feed that to my little brother. Explains a lot. I'm sorry again, Jim. You came out all right. So now what's probably the next one's a king. There's only 3 kings left, and there's only 51 cards left. That, of course I erased it. I'm really bad today. Remember how the part of the and was a given? This is the probably get a king on the second, given that I got a king on the first. That's why that changes. Because now it's dependent. Over there it was independent. Why? Because whatever I did, I reset. Over here, I don't reset, right? So this would be dependent. These changes. And then, whatever the shit that is. 0045? Okay. So then what would the probability of an 8 and then an ace be? There's one little difference here. Let's probably get an 8. 4 to 52, I throw that away. Right, my little brother's out. He's got a stomach ache for some reason. Let's probably then get an ace. Good, there's still all 4 aces, because I threw an 8 away. But there's only 51 cards because I threw a card away. So why did that top change? Because I threw that same thing away, but here, there's still 4 aces. I love it. And then whatever the hell that is.
0, 0, 6.
Bless you.
Thank you.
6-0? Okay. So try to do that second problem. We'll see how far we can get. The second problem about the this might have been some, getting some frustration out. Just imagine putting some politicians in a haunted house and just take them out and then put them back in and just let them scream. So try out a couple of these. We'll see how far we can get.